Good? All right, let's yeah. All right. Today, chapter 6 is about the mole. Do you remember the mole?
6.022.
The atomic mass is measured in grams per mole. You remember this? Okay. So, yeah, it's a unit that we use. It's the SI unit of amount of substance, but we can't measure it. There's no tool to measure the amount of moles. So what in the world? Why do we use it? We're going to talk about that today. Okay? So the mole is abbreviated, because it's such a long word, to MOL. So don't abbreviate the word molecule to MOL, especially in this unit. Well, forever actually. Okay? So 1 mole of anything is equal to 6.022 times 10 to the 23 particles of that thing. Doesn't matter what substance you're dealing with. It's the same for all substances. And this makes it very useful later on today. Okay? So in real life, we probably won't ever care about how many atoms there are in a substance. We don't care. But I'm going to show you how to figure it out. But there's a reason we're going to go over this. And it'll make sense a little bit later on. Okay? So first of all, I'm going to talk about representative particles. And I'm going to talk about 4 different types of representative particles. So what the heck is a representative particle? A particle that represents a type of substance. Okay? So if we're dealing with elements, then we call the representative particle of an element, what do you think? What represents an element?
Atoms.
An atom. You with me? Atom is the smallest particle of an element that still tells us it's that element, right? And then we have, if we have a covalent compound, we call these molecules. Kind of like we talked about molecular formula, molecular structure. That's for covalent compounds. And if we have ionic compounds, these are called, now a lot of times people in general will call them molecules still. And I don't care if you call them molecules, and you might. But the actual name is formula unit. And that's kind of long and clunky, so we abbreviate it. I'm sorry. And the last one are ions. And the smallest unit of an ion is an ion. Okay? if we have 1 mole of carbon, we have 6.022 times 10 to the 23 atoms of carbon. If we have 1 mole of water, we have 6.022 times 10 to the 23, what? Molecules of water. And if we have 1 mole of sodium chloride, we have 6.022 times 10 to the 23 formula units of sodium chloride. And if we have 1 mole of O2 minus ion, we have 6.022 times 10 to the 23 ions of O2 minus. We good? So we learned the 4 different types of representative particles, and that 1 mole of anything is 6.022 times 10 to the 23 of that thing, particles of that thing. We okay on that? All right. So that's our first conversion factor we're learning today. We need to know it, at least for this unit exam. Okay. Later on, maybe it might be on the final, I can't remember. But it will be on this exam. So the conversion factor is 1 mole of anything is the same as 6.022 times 10 to the 23 particles of that thing. And we can flip it. 6.022 times 10 to the 23 particles is the same as 1 mole. Just a conversion factor. And again, we don't care how many atoms there are in a penny, right? There's a lot of them, but we don't care. But what we do care is that it's the same number for every substance, for 1 mole of that substance. Okay? And we'll talk a little bit later of why that's important. Okay? So let's do some examples. If we have 7.303 times 10 to the 24 atoms of gold, I want to know how many moles of gold. I know what I'm looking for. I know what I know. So then I solve. Using the, what are we using here? How do we do this? You guys remember how to convert? What do we call this? Dimensional analysis. We good with this yet? This is all we're dealing with. And we'll be dealing with this the rest of the semester in this way. Okay? The way we're learning in chapter 6, this is the way we're doing it for the rest of the semester. Are we still going to have to convert milligrams to grams? Yep. Still have to know how to do that. Okay? So where do we start? With what we know. 7.303 times 10 to the 24 atoms of gold. Write everything out. Do I want atoms of gold in my answer? No, I want moles of gold. So I need to cancel atoms of gold. So where does it go? On the bottom. And we want moles of gold, so that goes on top. Anybody know the conversion factor? if we have 1 mole of anything, we have 6.022 times 10 to the 23 particles of that thing. Are we good? That goes away. That's what we're looking for, so we can stop converting. We divide, and we get 12.13 atoms of gold. Not atoms, sorry. Moles of gold. How did I catch myself? I looked at that. I saw the atoms cancel. Always write it out. And then you got to check. Okay?
Sure, where is the tentative date for the test? I saw it on the calendar, but I don't know if because of fall.
Okay, so the next exam covers chapter 5, 6, and 7. So we'll finish chapter 6 tonight. And then, so the exam, so this is exam 3, is on November 4th. Tuesday, November 4th in class. Unless you guys like the testing center better.
How many questions are like, because it's three chapters? So there's
20.
It's still 20, okay.
Yep.
So
So
there's more.
still don't miss any.
Yeah.
Otherwise it's 5% each. Oh. What?
Still be perfect. Fine.
All right. Any other questions? Okay, so let's do another example. Okay, how many chlorine atoms are there in 2.88 moles of silicon tetrachloride? Okay, where are we gonna start? With what we know, right? We know what we know, and we know what we're looking for. So use the problem-solving strategy always. 2.88 moles of silicon tetrachloride. Do I want moles of silicon tetrachloride in my answer? No, so it goes on bottom. And I am looking for atoms of chlorine. Ooh. Can I go to atoms of chlorine yet? Not yet. What can I go to? What do we call the particles of silicon tetrachloride? Almost. Atoms are the particles for elements. Silicon tetrachloride is a compound, and specifically it's a covalent compound. So what are the covalent compound particles called? Molecules, right? Don't abbreviate it, because then you'll just cancel everything out. And if I have 1 mole of silicon tetrachloride, how many molecules do I have? 6.022 times 10 to the 23 molecules. That goes away. Now, am I looking for molecules of silicon tetrachloride? No, so I put that on bottom. Do I know how many atoms of chlorine there are in 1 molecule of silicon tetrachloride? I hope so. How many? 4. Do y'all get that? Okay, just like in water, H2O, there's 2 hydrogens and 1 oxygen, right? In SiCl4, there's one sulfur, one silicon, and 4 chlorines. And we just care about chlorines here. So there's 4 atoms of chlorine. Does that make sense to everybody? Questions? Okay. Our unit is what we're looking for, so we can stop converting, multiply and divide, and we get 6.94 times 10 to the 24 atoms of chlorine. Questions?
Why is it 24?
Because when we multiply this value with this value with this value, that's what we get. I mean, do you want me, did you try typing this in? Do we all know how to do this? Okay, good. So 10 to the 23, if we just multiply by 10, we're going to get 10 to the 24. Well, what's 6 times 2? That's over 10. And that's why we get 10 to the 24. Good? Questions? All right. So like I said before, we can't measure moles in the lab. So we're going to have to convert moles to grams or grams to moles. We measure grams in the lab and we convert it to moles so that we can do some calculations. Why? Because it makes it so much nicer to do calculations, right? Wait. So we can make good predictions. Really, really accurate predictions, actually. Okay? The only way they wouldn't be good predictions if you didn't make good measurements. Okay? All right, so we talked about atomic mass measured in grams per mole, right? AMU is grams per mole. You remember this? Okay. And we also talked about molar mass last unit. This is the mass, of 1 mole of substance. So, for example, we kind of did this when we did intermolecular forces. You remember this? Determining which substance has a higher melting point or boiling point. And if they have the same intermolecular force, then we have to check their mass. Remember this? Okay, this is molar mass. So if we have water, for example, the molar mass is just the atomic mass of all of the atoms in our molecule added up. So what's the molar mass of hydrogen? 1.008. If you look on the periodic table. Does anybody need a periodic table to look at? If anybody knows, if anybody does, you can come grab one. Well, good? All right. So I want you to look these up for me. And then we're going to do what with it? Multiply it by 2, because there's 2 of them. And we're going to add to that the atomic mass of oxygen, which is 16. And that goes to 18.016 grams per mole. You with me? And what is this? This is just a conversion factor. Converting grams to moles or moles to grams. So we can write this as a conversion factor. 18.016 grams per how many moles? 1 mole. Or we can write it as 1 mole for every 18.016 grams of H2O. Good? This is how we go from grams to moles or moles to grams. Should we practice some more? Let's do it. How many moles per gram, how many grams per mole do we have for sodium chloride? What's the molar mass of sodium chloride? Everybody look it up for sodium. What is it? 22.99 plus 35.45. And we add those and we get 58.44 grams per 1 mole. And you can just write it grams per mole, but that's my conversion factor. Or the flip version, depending on what I start with, right? We good? Okay. So that's cool. Is molar mass very useful just to know by itself? It's not. We use it as a conversion factor. So let's do an example. If I have 1.58 grams of sodium chloride, I want to know how many moles of sodium chloride I have. This is what I'm looking for. This is what I know. So start with what we know and convert it. 1.58 grams of sodium chloride. Do I want grams of sodium chloride in my answer? Nope. Goes on the bottom. Moles on top. And what's the conversion factor? That we just figured out, but the flip version of it, right? If we have 1 mole, we have a mass of 58.44 grams of sodium chloride. Y'all with me?
Yes.
Too easy? Is that why we're not saying anything? No. Okay, I'm just kidding. Thanks for saying so. So grams of sodium chloride go away. We're left with what we're looking for, so we could just multiply and divide. In this case, just divide. And we got 0.027 moles of sodium chloride. Doing okay? And by the time we're done with this chapter, guys, we will be doing full problems that mean something. So we're not going to just do grams to moles and moles to grams. This is just one conversion. In the end, we'll do up to 3 today. 3 at a time. Or 1 at a time, but 3 in one problem. Good? 3? That's not too bad, is it? Have we converted a bit more than 3 before? Yeah. We've done this. So we only have 3. Are we okay so far with moles to grams and grams to moles? Okay, just make sure you're with me before we move on. If you're not, please say something. Okay? Let's do one more example. Let's say we have 2.45 moles of carbon dioxide, and we want to know how many grams of carbon dioxide I have. I know what I'm looking for, and I know what I know. What do? Start with
CO2.
what I know, yeah. 2.45, or we can find the molar mass of CO2. If you can see that, yeah, do it. What's the molar mass of CO2? Carbon is 12.01, not multiply, plus 16 multiply 2, and that gives us 44.01. Can I round that? Not if you want the exact answer. But listen, on the test, it's multiple choice. I'm not going to say one of the answers is 44.01 and another answer is 44. I will not. So, I always round. But, if you don't want to, then don't. But I don't round too much. For example, chlorine has a mass of 35.45. What does that round to? 35. That's kind of a lot. If you're going to round it to anything, round it to what? 35.5? It's like, how do I know? If you're not sure, guys, don't round. That's the easy way. Just don't round. Your calculator can do it, right? No big deal. Okay? So, for this class, I'm not going to round. Just because I think that's a good way to go.
I have a question.
Uh-huh.
Where'd you get the 16 from?
Good question. Thanks for asking. So, the 16 came from the atomic mass of oxygen,
Oh, okay.
and we just multiply that by 2 because there's 2 oxygens in CO2. Thanks for asking. Okay? All right, so we have 2.45 moles of CO2, and I don't want moles of CO2, so that goes on bottom. And I want grams of CO2, so that goes on top. And I know we have 44.01 grams of CO2 for every 1 mole. Moles go away. I'm left with grams. That's what I'm looking for, so I can stop converting. 2.45 multiplied 44.01, and that's 107.82 grams of carbon dioxide. How are we feeling? What?
That's better. More explain how you can,
Okay, good,
it's more clear than.
good. All right, so make sure we get this as we go so that you don't fall in the cracks. You fall in the crack, it's hard to get out if you don't say something. Okay, but if we're right there, we can help you get out. Okay? All right, let's do... Now let me show you why we learn moles. Okay, this is, and I'm going to prove to you why we can not have to worry about how many particles there are in a mole or in 5 moles. Okay, so let's talk about water for a minute. Water, we have 2 hydrogen atoms for every 1 oxygen atom. You with me? Can we say we have 2 moles of hydrogen to every 1 mole of oxygen? We can. We just bypass the particles and go straight to moles. So we can say 2 moles of hydrogen for every 1 mole of oxygen in water. You have to have water for it to be that, but okay. Now let me prove it to you. Can we say that for C3H8? 3 moles of carbon for every 8 moles of hydrogen? Yes, we can. Okay, and let me prove it to you so that you can maybe get that past you and you can just use it. All right, let's convert 2 atoms of hydrogen into moles of hydrogen. 6.022 times 10 to the 23 atoms of hydrogen on bottom so that it cancels to 1 mole of hydrogen. This is how we convert it to moles. You with me? So atoms of hydrogen go away, and we get 3.32 times 10 to the negative 24 moles of hydrogen. Yuck. Right? So now let's do 1 atom of oxygen and convert that into moles. 6.022 times 10 to the 23 atoms of oxygen so that it cancels to 1 mole of oxygen. And we get 1.66 times 10 to the negative 24 moles of oxygen. Now somebody calculate this for me. What is moles of hydrogen, the ratio of moles of hydrogen to moles of oxygen? What do we get? So 3.32 times 10 to the negative 24 divide 1.66 times 10 to the negative 24. 2. The ratio is 2 to 1. The ratio is 2 to 1. The ratio is 2 to 1. 2 to 1. And why does that work? Because we're using the same number to convert it to moles. Pretty cool, right? Now we don't ever have to use particles. We don't ever have to use particles, except for maybe one problem on the exam. Ekri.
Where did 6.022 come from?
Yeah, it comes, well, Avogadro found it, but it was there before he found it. Where did it come from? That is a wonderful question. We won't talk about it.
So then is it always just that number?
Yep.
Oh.
That's how many particles there are in 1 mole of anything.
It's like the rule, that 1 mole
And
is
we
always
will
gonna
talk
be
about that.
And it's like,
Because we don't know.
Yep, that's the way it is.
We don't know where it came from. Well, we have predictions, but or hypotheses, but yeah.
so then on the test, would that one just be given?
No, you need to know it.
But you're gonna use it a lot to practice, so you're gonna.
But let's see. Let's see. Are we given this? Let's see. You guys have a periodic table?
I doubt it.
Oh, it's on there.
No way.
Ah, it is on there.
Yeah, it's gonna be.
But you have to know where to find it. Maybe you ought to look at your periodic table.
Yeah.
Oh,
Shocker.
what do you mean? You always have to memorize everything, don't you?
Yeah.
Ah.
My
So-
brain can only handle so much.
That's why we gave that to you, because we knew you could only handle so much.
So helpful. So helpful. So generous.
You're welcome. Okay.
Teacher, can you explain again before we continue?
Explain what?
The minus 24 is from the one that is in blue, right?
Yeah.
That's why it's minus 24.
Why is it minus 24?
Uh-huh.
Because we're dividing by 10 to the 23.
Mm,
We're dividing by 10 23 times. If we divide 1 by 10, divide 1 by 10 one time, we're going to get a smaller than 1 number, aren't we? 0.1. If we do it by 10, 24, 23 times, we're going to get a really, really, really small number. Hence, we get that. But our calculator will tell it to us. Okay? We don't have to be able to do, I mean, it's nice to be able to know that. It really is, to be able to calculate this without a calculator. You can do it. But it's nice to be able to use a calculator too, right? But what happens when we divide the 10 to the 24? They go away. So really it's 3.32 divided 1.66, right? And we get 2. Okay, are we good there? So I went over that so that we don't ever have to do it again. Never. We're never going to do this proof again, ever. Okay? We might have to convert moles to particles and particles to moles one time on this exam, but that's it. Any questions? So we learned how to convert from moles to particles and particles to moles. And we learned how to convert from grams to moles and moles to grams. 2 conversions so far. Where do you find your moles to gram conversions? On the periodic table, the atomic mass added up for each atom in the molecule, right? Or in the compound. And the particles to moles, you're just going to have to, in fact, you don't have to remember that. It's on your mole roadmap. Did you guys all see the mole roadmap? Maybe I should talk about the mole roadmap real quick. I will show you how to use this once we learn everything, but would it help to show you how to use it right now? Or should I wait? I'll wait. All right. There's not any questions. We all get, in fact, should we practice some of this stuff before we move on? Okay, on section 1 and 2 on your worksheet, section 1 says calculate either atoms to moles or moles to atoms. No, this is all particles to moles. No, moles to, no, it's both. Yeah.
I have a friend, and in her chemistry class, moles are 6.02, and you're allowed to answer with that. Is that okay to use for like all the questions, or should we do 6.022?
Let's see. I would use 6.02.
Doing the homework.
Is it?
Yeah.
Okay. Yeah, that's probably fine.
Oh.
But I think on the exam it's 6.022. But again, it's just a rounding thing. It should be fine.
I asked because there's one of the questions, there was like moles in 7.35 atoms of sodium. That there's like actually different answers within the first 3 digits.
I would go with 6.022.
Okay.
Does anybody want to go over one of these together, or we want to just try it on our own? Together? Yeah. On section 1 or section 2 or both? Okay. You tell me which one. Do you want to go from moles or atoms to moles or molecules to moles or ions to moles or what? Which one of these do you want to do? Not all at once. I really don't care. Do you care? Let's go ions to moles. I want to know how many ions in 0.38 moles of NaNO3. Where do I start? With what we know, right? 0.38 moles of sodium nitrate. And we got to convert this to what? Particles. Y'all with me? So moles of NaNO3 go on bottom so that they cancel. And what's the particles of NaNO3 called? Are they called ions? They're not. What are they called? Formula units. Because this is an ionic compound, right? So we have formula units of sodium nitrate. If we have 1 mole of sodium nitrate, we have how many formula units? 6.022 times 10 to the 23. You guys are so ambitious tonight. Just kidding.
Fall break wasn't long enough.
Oh, I know. Okay. And so we're left with formula units. Is that what we're looking for? No, we want number of ions. If we have 1 formula unit of sodium nitrate, how many ions do we have? 2. We have a cation and only 1 anion because there's no parenthesis. You with me? No? This sodium nitrate is made up of 1 sodium and 1 nitrate. There's not 3 nitrates because that 3 is a part of nitrate because there's no parenthesis around it. Do you remember doing this? Okay, so there's two ions, and we don't care what type of ion, it just says number of ions. So we have 2 ions for 1 particle of sodium nitrate. So we're going to do 0.38 multiply 6.022 times 10 to the 23, multiply 2. And we get 4.58 times 10 to the 23 ions. How are we feeling? And if we do the one on the top right, number of carbon atoms in 2.2 moles of C3H8. That one's similar. How many carbon atoms do we have in 1 particle of C3H8? 3 of them. Do you see that, guys?
What was your question there, so I understand?
So on the top right question in section 1, it says how many carbon atoms are there in 2.2 moles of C3H8? Well, eventually we're going to have to convert moles to particles of C3H8, right? And then particles of C3H8 to atoms of carbon. So how many atoms of carbon are there in 1 particle of C3H8? 3 of them. C3, 3 carbons in 1 C3H8. Do you get that? All right. Which one from section 2 do you want to do? None?
The second one down.
Oh, second one down on the left? Okay. So we got NH4 in parentheses 2 SO4, and we got to calculate the molar mass. We can do this a couple of ways. We can calculate what it is for NH4 and then multiply it by 2. Or we can just say, okay, what is it for, what's the molar mass, what's the atomic mass of nitrogen? 14.01. And how many are there? There's 2, because that 2 goes to everything in that set of parentheses, right? Multiply that by 2, and we have hydrogen is 1.008. Multiply how many? 8. Y'all with me? Plus sulfur is 32.07, I think. I don't have that memorized. It's just used it earlier today. Plus oxygen is 16 multiply 4. You get that, everybody? So you multiply that and you get 28.02. Multiply that and you get 1.064. And then plus 32.07 plus 64. You add all those together and we get something. Thank you. And we get 132.17 grams per mole.
Where's your
What's that?
the 8?
This 8 right here?
Yeah.
Because there's 2 NH4s, right?
Yeah.
And every one NH4 has 4 hydrogens. But there's 2 of them, so that means we have 4 more. That's a total of 8. Easy way to do it is just to multiply. Good? Thanks for asking. Anything else?
So similar thing on that third one from the top. CU.
Yeah. So there's going to be 2 nitrates, 2 NO3s. So you have to multiply that 2 to each one. So there's going to be 2 nitrogens and how many oxygens? 6. That's it. We good? All right. Let's move on to the main topic of the night. Woo-hoo. But this is going to help us really. So we learned 2 conversion factors, right? All we have is 1 more. And then we have all the conversion factors for chapter 6. That's 3 total, like I promised. Okay? So here we go. Stoichiometry. Sounds scary. It's not. It's really not. All it means is the quantitative relationship. What does quantitative mean?
Number.
The amount, right? Quantity. The quantitative relationship
How do you say that?
stoichiometry, yeah, between reactants and products. You guys remember where the reactants are? On the left side of the reaction. Products are on the right side. In a chemical reaction. All right, so let's start with, so basically it helps us to convert from one substance in a reaction to a different substance. And it could also be between two reactants and also two products. It doesn't have to be just between reactants and products. Okay? So if we have C3H8 plus O2 gives us carbon dioxide and water. And if you remember, this is a combustion reaction or oxidation reduction reaction. Okay, now, this equation without being balanced is almost worthless, guys. You must have a balanced equation from here on out. Okay? We all good with balancing equations? All right, so where are we going to start to balance this? Carbon, hydrogen, or oxygen?
The biggest one.
Yeah, we'll start with hydrogen. There's 8 on the left, so what number goes here to make 8 on the right? 4. That gives us, let's see, now let's do carbon. We have 3 on the left, so we need a 3 right there to have 3 on the right. Now let's count the oxygens. How many here? 6. How many here? That's a total of 10. So what number goes right there? 5. We good? Okay. So you have to have a balanced equation from here on out. What's that?
That first you have to have a balanced equation.
Yes. In fact, let's, yeah. All right, so let me show you the conversion factors from our balanced equation. So in this particular equation, I'll give you, there's 12 conversion factors. 12. Do you have to memorize them? No, you just have to know how to find them. Here we go. So we look at the coefficients in our balanced equation. What's the coefficient in front of C3H8? 1. So for every 1 mole of C3H8, we have 5 moles of O2. Do you get that? That's one conversion factor. What's another one that looks just like that one almost? You flip it. You flip it. So that's really 2 conversion factors. Is that okay if I don't write it? Or do you want me to? I will. Flip it. You want me to write it?
Yes.
Okay. So the other one that's equal to this is 5 moles of O2 for every 1 mole of C3H8. Do you get that? I just flipped it. Now can I erase it? Okay, another conversion factor is for every 1 mole of C3H8, that's this one again, we get 3 moles of CO2. Okay so far? And again, for every 1 mole of C3H8, we get how many moles of water, guys? 4. That's the coefficient in front of water. And then we have the flip version of those. Okay, and then, so that's 6 total, yeah? That means we have 6 more. Here it is. 5 moles of O2 for every 3 moles of CO2. And 5 moles of O2 for every 4 moles of H2O. And the last one is 3 moles of CO2 for every 4 moles of H2O. Does everybody understand how I got those?
Every combination.
Yeah, that's every combination, and then you flip all of those, so that's 6, and there's 6 more if you flip them. Now, you don't ever have to do what I just did, ever again, if you understand it. Can you come up with those? Or do we have a question? Okay? Now let me give you the steps for stoichiometry. There's only 4. In fact, I can give you steps, or I can show you how to use this map. Question?
Could you just slow it down just a little bit? I just wanna look at it.
Uh-huh. So 5 oxygen to every 3 carbon dioxide. It's just coefficient ratios. That's it. 5 oxygens to 4 waters. 3 carbon dioxides to 4 waters.
Okay.
Good? All right. I am going to show you how to use how to use this mole road map that you get on. This is your reference sheet that you get on every test. Okay? This was on the back in the testing center, right? Okay. So I'm going to write it just like it is on here. We got grams of substance A. And if I want to convert from grams of substance A to moles of substance A, what do I use? Molar mass. And if I want to go from moles of substance A to particles of substance A, or vice versa, then I use Avogadro's number, 6.022 times 10 to the 23, and that's written on there for you. And then if I want to go from moles of substance A to moles of a different substance, we'll call substance B, then we use the mole to mole ratio. That's found on balanced equation. And that's what we just barely went over. So this is the mole to mole ratio, 5 moles of oxygen to 4 moles of water, for example. Good? And then we just do that exact same thing. If I want to go to moles of substance B to grams of substance B, I just use the molar mass. If I want to go to moles of substance B to particles of substance B, I use Avogadro's number. 6.022 times 10 to the 23, and molar mass. We good? So now let's talk about the steps to stoichiometry. Step 1. This is the most important step. If you don't do this step, you're going to get it wrong 99% of the time. This is balance the equation. Step 2 is we convert given substance, whatever it is, into moles. Whether we have grams of substance A or particles of substance A, we're going to convert that to moles. Always. Always go to moles. If we already have moles, we can skip that step. Good? And then step 3. Any ideas what we do once we're at moles? We convert to moles of our desired substance. Convert to moles of desired substance. What do I mean by desired substance? Yeah, what is the question asking for? What substance are they asking for? And then step 3 is to do what? Go to desired unit. Convert to desired unit. Does that make sense to everybody? By looking at the mole road map? Okay. The only thing that's not on the mole road map is balancing equations, so make sure you do that first. Otherwise, it's always going to be a 1-to-1 ratio. And it's not always going to be a 1-to-1 ratio, guys. Sometimes it is, but not always. So just make sure you have a balanced equation. You ready for a real problem? Almost a real problem. We'll start simple, and we'll build and build and build. 3 steps. We're going to start with 1 step. All right, so we have an equation, FeCl3, and it decomposes into iron and chlorine gas. So let's balance it first, because we know we have to do it. What goes in front of FeCl3? 2, because there's 3 here and 2 over here. We use least common multiple. Since we have 2 in front of the iron, so we better have a 2 in front of that iron. We good? Okay, now the problem, we'll say in words, we have 13.5 moles of FeCl3. We want to know how many moles of Cl2 are produced. So this is the way I do it. And you don't have to do it this way. But I write down what I know right underneath the substance. I have 13.5 grams of FeCl2. Now, I usually don't write FeCl3. I just write, okay, I have 13.5 grams of the substance that I put it under. This is the way I do it. You do not have to do it this way. Just saves me some writing. That's all. Okay? And I want to know how many moles of Cl2. So I put that question mark underneath what I'm looking for. Does that make sense why I do what I do? If you wanted to, you can just write it out. Okay, what do I know? 13.5 grams of FeCl2. What am I looking for? How many moles of Cl2 are there? I can just do it that way if you want. Just the same way we've been doing problem-solving strategy. We good? Anybody hate the way I do it? If you do, I won't do it anymore. Okay. Okay, so now what? This is where I gotta go, and this is what I know. I always start with what I know. We start with 13.5 grams of FeCl3, and I don't want grams of, in fact, oh, it's not grams. Is it grams? No, it wasn't grams. My bad. moles. Okay. So first step is balanced equation. We did that. Second step, convert to moles. We're already at moles. We're done. Third step is to convert from moles of given substance, which is FeCl3, to moles of desired substance, which is Cl2. Yeah. I need to remember to plug this in after my first class. All right. So now we're going to use the mole-to-mole ratio. What goes on bottom? Moles of FeCl3. And what goes on top? Moles of Cl2. What I'm looking for. We good? Questions? All right. Now what's the mole-to-mole ratio? What goes on top? I want moles of Cl2. Here's Cl2. How many? 3. Are we good here?
Yeah, we
Uh-oh. Why can't you? Okay, sorry. All right. So we all good with 3 there? How many moles of FeCl3? 2. Questions on that? So moles of FeCl3 go away. We're left with what we're looking for, so we can stop converting. So this is just a 1 conversion. 13.5 multiply 3, divide 2, and we get 20.25 moles of Cl2. Good?
Yes.
Are we good with moles to moles?
Yeah.
Okay, so that's just one. That's the middle conversion factor that we'll do in the very end. So in our whole big problem that we have 3 steps, that's our middle step every single time.
Would it ask you for just what the mole of Cl would be? Do we have to divide that in, because there's 2 of them, for just find the 1?
Good question. Ladies and gentlemen, whenever we do mole to mole, we only use the coefficients. And we only use the coefficients for mole to mole ratio. Period. Never anywhere else. Okay? That's what we use a balanced equation for. So, the reason I'm saying that is because some people say, okay, we start with 13.5 grams of this. Do we have to multiply it by 2 because there's 2 there? No. The answer is no, never. Okay? That 2 is only used for the mole-to-mole conversion. So thank you for asking that. We good? All right. If we don't need any more practice from mole to mole, then I'm going to go, now we're going to do a 2-step problem. And if you do need more practice, we can always do one, or you can do some on the worksheet. Okay? Okay, let's go to another example. So if we have Al2O3 and it decomposes into aluminum and oxygen gas, remember if it says oxygen it means O2, right? Because that's one of those diatomic molecules. And it says how many grams of aluminum, so I'm going to say grams equals question mark underneath aluminum, are formed from the breakdown of 12.4 moles of aluminum oxide. I wrote it. Wait for it. Okay. We good? Okay, what's my first step? Balanced equation, always, always, always. So where should I start? Aluminum or oxygen? It doesn't matter. Should we start with aluminum and see what happens? Okay. So we got 2 aluminums on the left. How many on the right? 2. Okay. We got 3 oxygens on the left. How many on the right? Oh, so what do we need? 1.5? We could. We could do 3 halves, right? Because 3 halves times 2 is 3. But then what do we have to do? Multiply everything by 3, right? Or 2, right? But if we start with the one with the most first, it'll make so we don't have to worry about that. Sometimes, not always. We have 3 oxygens on the left, 2 on the right. What happens when we have even and odd? Least common multiple is 6. So I'm going to multiply that one by 2, this one by 3. My oxygens are good. And now I have how many aluminums on the left? 4. You can do it either way, guys. You can. Right? You can. You just less messy this way. That's all. But you can erase. No big deal. All right. Now what do? We balance the equation. Now we convert given substance, which is 12.4 moles of O2 into moles. Oh, it's already there. Not of O2, sorry. Al2O3. We already have moles, so we're done with step 2. Step 3 is convert moles of given substance into moles of desired substance. What's our desired substance, guys? Aluminum. So we have 1 mole of aluminum, or of aluminum oxide. Uh-oh. My bad. What's the mole-to-mole ratio, guys? Where does the 4 go? Next to aluminum. And what goes here? 2. Even sometimes I make mistakes, don't I? That's why you got to watch what you're doing, pay attention, and make sure they all cancel out correctly. Okay, so now we converted to moles of our desired substance. Now we convert to desired units. So moles of aluminum go on bottom, so it cancels. Grams of aluminum go on top, because that's what we're looking for. And what's the molar mass of aluminum? 26.98 grams per 1 mole. Everything cancels except for what we're looking for. So we're done converting, and we get 669.1 grams of aluminum. Doing okay?
Yes.
Okay. can I go from grams of aluminum to grams of oxygen, or moles of oxygen? The same way, right? So the mole to mole ratio here is 4 to 3, exact same way. Are we good, or should we do it? Okay. So if I have 669.1 grams of aluminum, and I want to know how many moles of oxygen I get, I'm going to convert grams of aluminum into what? Moles. Can I use the mole roadmap to guide my thinking? Yeah, look at this. I start with grams of substance A. Could I start with grams of substance B instead?
No.
Sure. Why do I say A and B? A is one substance, B is a different substance. A comes before B, so that's why I do A first, but it doesn't matter, okay? So I start there, and where's the only place I can go, guys? To moles of that same substance. Once I get there, I got to go to moles of my different substance. This is what I'm looking for. 2 steps. 1, 2. You good? Does that make sense using the mole roadmap? All right. So we need to find the molar mass of aluminum. That's the same thing, 26.98 grams of aluminum on bottom, so it cancels, to 1 mole of aluminum on top. And the mole to mole ratio from aluminum to oxygen is 4 moles of aluminum to 3 moles of O2. And that gives me, I don't have this answer, 669.1 divide 26.98 multiply 3 divide 4 gives me 18.6 moles of oxygen. We okay? Yes? No? Okay. Okay, ready to step it up to the next step? 3 conversions?
Okay, I found this on the web for conversions. Check it out.
No. Okay, sorry about that. I didn't even say theory. Okay. All right. Do you want to see if you could do this last one on your own? I bet you could. Use the mole roadmap. Use the steps. I bet you could do this. Try it. So we have K2SO4 plus BaCl2 gives us KCl plus BaSO4. And the problem says, what mass of K2SO4, so mass is grams, generally. If it doesn't tell you, then it's grams. Reacts with 29.8 grams of BaCl2. So we're looking for grams, and we have grams of BaCl2. We good? Try it. Or should we map it out on the mole roadmap first? Should we do that together? Here we go. I start with BaCl2. Should I call that A or B? It doesn't matter. But I usually call it A because that's what I start with, right? But it really doesn't matter. So I start here. Then I use the molar mass to convert it to moles. Then I use the mole to mole ratio to convert it to moles of potassium sulfate. Then I use the molar mass to convert moles of potassium sulfate into grams. So we got 1, 2, 3 steps. Does that make sense how to use this map, guys? Okay, it might take a little bit to get used to, but so go for it. I know I can do it, and I know you can do it with my help. Now let's see if you can do it by yourself. Yeah.
It creates 29.8 grams of what?
Of what?
What is the thing we're trying to find after we balance the equation?
Yeah, did you guys remember to balance the equation? Good. So we start with 29.8 grams of BaCl2, and we're looking for grams of K2SO4. That's it. If we balance it, we should get a 2 right here, and that's it. Is that what you got? Okay. Again, make sure you balance it first. If you don't, well, in this case, it would probably be okay, wouldn't it? Will we know it's okay? Not unless we balance it. So always balance it.
Oh, that was aggressive, I'm sorry.
How are we feeling? Any questions so far? Who needs more time?
I just get lost a little bit in the first, like, I understand everything, but just in the first step, where did you get the 29.8?
That was given to us.
Oh, and the problem there.
Uh-huh.
So how many grams of K to
Yep.
potassium?
Sulfate, uh-huh.
Sulfate we have for 29, okay.
Yes.
Okay, so that's how.
Yep. Did that help?
Yeah, because it was like, where that came from.
Yeah, so that was given in the problem.
And the problem, and then, yeah, we follow.
How are we feeling, guys? Give me hallelujah if you got this.
Hallelujah.
Oh, good. I'm teasing. Questions? Okay, so that is as hard as it gets for this chapter. In chapter 10, we're going to go a little deeper. And probably next unit will go a little bit deeper. But I'm not saying we're going to do 16 conversions. Probably still maximum 2 or 3. Maybe 4.
When we get into like the pH and stuff, it's like
Yeah, that's where it gets a little bit more. That's chapter 10. But
Acid and base.
it's not as bad as, well, we'll see. Any questions before we move on? You following this? Okay. Okay, I'm going to do one more, and then we will do our last topic for tonight. Oh, you need this still? We all good? Okay. So I'm going to use the same equation, K2SO4 plus barium chloride gives us 2KCl plus barium sulfate. And I want to know how many grams of barium sulfate will I get if I start with 20, I'm going to start with the same amount of this last one, 29.8 grams of barium chloride. So that was given to me in the problem. So we're going to start with 29.8 grams of barium chloride, right? And the first step is just copy, right? Y'all with me?
So we're taking, we off from the previous?
No, I'm just starting
Oh, sorry.
with what the same number here. Same amount. So it's 208.23 grams of barium chloride for every 1 mole of barium chloride. We all good with that step? Okay. And then we go from moles of barium chloride to what? Look at at our mole roadmap, guys. We're starting here, and we're going to here. We did molar mass, right? So now what do we do? Mole to mole ratio. What's our desired substance here? BaSO4 is our desired substance. And what's the mole to mole ratio from BaCl2 to BaSO4? Oh, it's also 1 to 1. That's nice. And now I got to convert moles of BaSO4 to grams of BaSO4. So we got to find the molar mass of BaSO4. 137.3 plus 32.07 plus 16 times 4. Did I already figure this out? No. What is it?
174.27.
Grams of barium sulfate to 1 mole of barium sulfate. That goes away. Multiply and divide, and what do we get, guys? 24.93? 94? Grams of barium sulfate. Okay, ladies and gentlemen, this is called my theoretical yield. Why do we call it that?
Because in real life you make mistakes and things like vanish.
Yeah. In theory, this is what we should get. Yeah? If we do everything perfect in the lab, this is what we should get. Okay? This is the maximum amount of product that we should get in theory. We good? Okay. One more term is actual yield. Actual yield is the amount of product that we actually get. We good with those terms? All right, now for the last topic, percent yield. Now, ladies and gents, I can give you an equation for percent yield, but percentages are percentages are percentages. They're always the same. How do we calculate our percentage on a test, guys? The number we got correct, because that's what we're interested in, right? Divided by the total, the amount we could get correct. Then to change that to a percentage, we multiply it by 100%. Okay. Now in chemistry, how much did we actually get? The actual yield. How much are we trying to get? The maximum. all of it. Total theoretical yield. Then times that by 100%. And that's it. So let's say in class or in lab, I got 20.5 grams of barium sulfate. That's how much I actually got in the lab. In theory, I should be able to get this amount. Uh-oh. Oh. What amount should I be able to get, guys? 24.94 grams. In theory, that's what I should be able to get. Ah. One more time. So what we actually got divided by what we should be able to get, 24.94 grams of barium sulfate. And what cancels? Grams of barium sulfate, and then don't forget we got to multiply it by 100%. And what do we get? So on the test, I will give you the actual yield. You won't have to go to lab and get it. Okay? What do we get, Ewing?
How many decimals we need to know?
What does your calculator tell you?
It's 0.8219.
Did you forget to times by 100?
So it's 82.197277.
82.2 is good enough.
82.2? Okay.
Yep. Does that make sense to everybody? Can we all do this? That's just to tell us how good we did on the lab. Just like a test. Can you find your percent error, guys? (100 minus 82.2), right? And that's your error. All right. Any questions? That's all I have for you tonight. If you don't have any questions, then have a fantastic night and drive safe. But if you have questions, I'm still here.